semester presentations, second day, second round. Thank you everybody for joining us today. Pleasure to see a lot of people. And without further ado, let's pass it to Shim to talk about his very fancy LiDAR systems.
So good afternoon, everyone. Today's topic is bidirectional generation between images and point clouds using Multiview-to-Lidar dataset. So this research started out as a question of, if you're in a self-driving system, like Waymo, for example, you're in the highway, and something happens. You're in the US. One time I was driving the highway, I swear to God, I saw a ladder in the middle of the street. God forbid that an autonomous car hits it for some reason, and one of its systems goes out. Or you're in the debris of an accident and your LiDAR system goes out. What do you do? In most ideal scenarios, self-driving cars are trained to stop on the side, turn on its blinkers, and give the control back to you. In case of Waymo, that's a bit difficult because there's no control on the vehicle side. So what do you do in that case? Highways is not an ideal place to turn on your blinkers and go to the side. That is sometimes not possible. Some areas or some streets are not just too narrow and then it's too dangerous. So our idea was, if I were to blind one eye, your performance would go down, right? Hallucinations would probably go up and you probably do the wrong decision. What if I'm able to regenerate the same data, but from a different perspective and historical data? In this case, we can generate LiDAR from images. In other cases, we can generate images from LiDAR and other images. This is the Argo2 data set. The Argo2 data set is a set of images and LiDAR points and timestamps across different cities. And as you can see, we have 7 directional images. And then we also have our LiDAR maps, or what we call as point clouds. Our attempt was to try to have a cross-generation modality, where we train models to generate one format from the other, and etc. So this is an example. This is an example where we train a model, given a LiDAR map, and given a direction flag. This is what we call multitask learning, where a model is given a task of doing multiple things. In this case, it's to generate images of different directions. That given a LiDAR map, generating the front side of the camera, the left side of the camera, right side of the camera, and the back side of the camera. This is the result, as you can see. It's a bit blurry. Now, the reason why at the time we did not consider this was, number one, LiDAR does not have color. But what you can see is some information about the street and the sky on average. So you can see some form of building, some form of sky, some form of pavement, but that's about it. So one fixing that we're going to be introducing probably was going to be adding temporal data, meaning that images from previous timestamps on one hand, and the other hand is to add data from different perspectives, like the left side, the right side, etc. We also tried generating point clouds from cameras. So given 7 directional images, generate a larger cloud point. And for that we had a bit of a doozy because it's quite a very, very tedious task. 7 images to LiDAR is quite expensive and quite hard. It wasn't as simple as we thought it would be. So we really had to get creative with this one. We tried different architectures from diffusion, CGANs, conditional generative serial networks, and autoencoders. And what worked best from what we discovered was something called variational autoencoders, or VAEs. Has someone heard about what a VAE is? You have. I've seen your projects, guys. Pretty cool stuff. So, surprisingly, or not surprisingly, sometimes diffusion may fail to encode spaces. Essentially, diffusion it's a state of the art of generating data. If you have seen Sora, if you have seen different models, those all are made by using something called denoising. Now, when we tried to implement that technique, that did not quite work as well. Specifically, we tried to do something called contextual denoising, and we're going to get to that in a second. But variational autoencoders did very, very well, surprisingly. So that was our phase 1. Our phase 1 was to do the following. Instead of having 7 images, giving it to its model, and then somehow, some way to predict the full LiDAR map, why not simplify the task? Why not create a input in, output out, the same thing, but you try to compress the data into this Latin dimension? Essentially, instead of predicting 10 million or 100,000 data points across 3 dimensions, I just need to predict 756, and that's about it. It's more efficient, much more clean, and much more, controllable. We also tried something called transfer representation. Now, who has heard about transfer learning? Raise your hand up. Okay. Have you heard about transfer representation? So transfer learning is when I take a model that was trained on task A, for example, identifying what a dog is and what a dog isn't. A transfer learning is now taking that same model, that trained model, and training it on identifying cats. That's called transfer learning. In this case, we did something called a bit different with this transfer representation. We had two pre-trained models. One is called DNV2 by Meta, the other YOLO V5 for object detection and localization. And what we essentially did is this. If DNV2 can capture depth for images, and then YOLO V5 can capture objects and their positional relative from the ego vehicle, what we're trying to simulate is, I've given you the objects in the images of the 7 directions. I've given you the depth and how deep or how close these images are or objects are. Generate the cloud points from those 2 data points. We implement something called feature fusion and feature representation. So essentially is you take the activations of DNV2, intermediate activations, and then YOLO V5, like you see from here, and concatenate them from the feature space. And then this is like an embedding, by the way. If we look at BERT embeddings, for example, that is a proxy way of how they do a pre-training task and then they do this, essentially. Anyways. We also apply self-attention and cross-attention. Do you guys know how the transform architecture works? So to fuse different data formats or different data representations, we apply something called attention. In essence, we're asking the model, given the embedding of this image and that image and this image and that image, understand how is this image related to that image, how is that image related to this image, and how is this image related to that image. This is essentially what we're doing. This is called same modality self-attention, because they come from the same dimensional space, same modality space. The same goes for YOLO V5. Once you have encoded that, we do something called projection, so you can align the feature space. And then now we do something called cross-attention. Cross-attention means that usually, it's in the decoder architecture of transformers, but in our case, we're essentially saying we're combining what you understood from the depth image and what you understood from the object's image, and now tell me, what did you understand? Yeah, 3 minutes, okay? So remember our variation autoencoder? So we trained that first, we froze it, then we attempted to train our model the following way. Given the images, 7 directions, given 2 models, given the embedded, we concatenate them, we predict the latent dimension, given the LiDAR, the encoder, and predict those. See what we're doing here? Essentially, we're freezing the encoder, we're just training it as a label generator. It compresses all the data into a latent dimension, and we try to predict that, and that's what we train. Page 3 is that once we have a convergence that is quite good enough, we use the decoder and then we predict the latent dimension. And let me show you guys the results. Thank you very much. So this is the results when we first started this project. You can see there's a straight line. I'm going to show you next what we have. This is what we have right now. What you see here is what has been generated from images. What you see here is what has been generated from the variation of the encoder. It's still a long way to go, but at the very least what we have now is that it's able to understand the street direction, the environment direction, which is a very good start. One of the things that we're going to do is we're going to try to make it more sensitive towards objects, and the way we're going to do that is called by adversarial learning, where essentially we have the original point clouds, and we have this, the generated point clouds, and we're going to pass it through an object detection and localization framework. And then they're going to compete against one another to try to get the maximum scores, essentially. Another thing we've been exploring with is actually, instead of trying to generate directly from one modality to another, we do intermediate modalities, which I'm going to skip for time's sake. But here's some mini surprises that we try to discover. We try to test how good our methodology would be by pre-training tasks. So essentially, pre-training task is to do one task before the aligning features and whatnot. But here's a good example. Anyways. So we trained something called a VLM-like. So do you guys know what a VLM is? It's called a vision language model. Essentially, you give it an image, you ask a question and answer the question. In this case, we pre-trained on how many cars are visible. Prediction was 7, character is 8. How many buses are visible? Our prediction or multiple is 1, the graph was 0, but what do you see over here? You see a plus. And etc. etc. So with that was some pleasant surprises. We're trying to do essentially an intermediate generation. So give an inscription, generate that data model. So just to play with things. And this is some of the diffusion results for text to images as well. And I'm going to end it with there. And I give you too much to TMI, but yeah. Thank you very much.
Thank you. Let's do a couple of questions. If there is any questions.
Yes.
How do you handle nighttime scenarios?
Sorry?
How do you handle nighttime scenarios?
Nighttime scenarios. So we do have so our University does not have nighttime. It does have a bit of a setting sun scenario, but doesn't have nighttime, luckily. But KT and BDD 100K, BD 100K does have night. And for that, they do have labels for that. They tell you if it's dawn, dusk, or, sorry, wrong word, but essentially they do tell you. And you can filter that on the labels basis. Any other questions? But for night times, by the way, our system is trained on daytime. That is a very good point. In nighttime, it's a bit difficult, it's more tricky, unless you have specialized hardware like cameras, night vision. That's quite tricky, but again, whenever there is data, you can do whatever you can. Any other questions? Yes.
So what's your, it sounds like you explored a lot of technology, and what do you think, where do you think the project is going to end? Do you think you're going to end this semester, or do you think it's going to go beyond that? Do you plan to carry work? Do you plan to keep working on it, or it's just a fun side hustle you have for this semester?
Allow me to quote Queen Latifah. Hell no, we're not gonna do it till next semester. We're gonna try to finish this semester. But yeah, so we're gonna try to finish this semester. Are we gonna finish on time? I don't know. I really, really hope so. It's a business project. There's a lot of moving variables. But once we become to know data a bit better, once you're more accustomed to your training sets, your test sets, the labels, it's gonna be a bit more easier to, and especially if you have GPUs like A100.
Yeah. All right. Any more questions? Thank you, then.
Thank you very much.